Hey, this is Lachlan Povins. This is my Physics 2211 Lab 3 Black Hole and Orbits. So, on to the introduction and main principles. For part 1, we're going to calculate the mass of a black hole given a known mass of an orbiting star. In this lab, we demonstrate the principles of universal force of gravity with F-net parallel and perpendicular components. And in part 2, we find stable orbit of a spaceship around a planet and moon by adjusting initial velocity. We also in this lab demonstrate the influence of a multi-body system on the orbit. This is all completed and done through GlowScript. So continuing off of that, in part 1, we use GlowScript to find the mass of the black hole by utilizing Newton's second law. And then F equals dp over dt, and force equals the force of gravity. And part 2, we use mass to determine the velocity of the spaceship required to orbit the moon and planet without crashing. We also use momentum. So for the code part 1, we used a while loop in GlowScript, and we first found v initial and v final. And from there, we went to momentum initial and momentum final using the mass of the star times the initial velocity and mass of the star times final velocity. From there, we found the change in velocity doing just v final minus initial, and the same with momentum. We did the momentum final minus momentum initial. From there, we got dp dt is the change in momentum over the change in time, and we set that equal to f net. From there, we calculated p hat and got the magnitude of p hat, and using the magnitude of p hat multiplied by p hat, we got dp dt parallel, and from there we can set f net parallel equal to dp dt parallel. And to calculate dp dt perpendicular, we set it equal to dp dt minus dp dt parallel, which gave us f net perpendicular equals dp dt perpendicular. And so then on to calculating the mass of the black hole. We ended up calculating the mass of the black hole at each step of the orbit. So to determine the actual mass, we had to take the average at each step around the orbit. And for the average mass of the black hole, we got 1.41 times 10 to the 34th. So now on to the code for part 2. We first put the mass of the black hole from part 1, as you can see on the bottom. And then I also adjusted Tmax to be a little higher so we can get the planet around the black hole. And then we used the Fnet of the planet, so the regular g m1 m2 over r squared times the vector. And then finally, we used the velocity and position update formulas. So to visualize this better, you can see that the middle dot is the black hole, and the cyan line going orbiting is the planet, and the purple line is the ship, which is orbiting the planet. And uh, with messing around with different ship velocities, we were able to make the ship orbit the planet without crashing or stopping from orbiting the planet. So for the what does it mean, in the instructions it said, in your analysis, you should discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. While in reality, both are mathematically the same. The rate of change of momentum is easier to calculate, as all we need is the system's change in velocity. And also, the net force requires us to take into account every factor exerting a force onto the system. Finally, onto the what if. If you wanted to predict the motion of the entire system, what would you need to include in your computational model? First, we would need to find all the individual forces and components acting upon each other in the entire system. Then, some objects may be more dominant because of their mass, such as the black hole has a way bigger mass than the planet and the ship.